This lecture focuses on how we move from the continuous time Fourier transform to the discretized time Fourier transform. So the Fourier series and the continuous time Fourier transform basically only operate on continuous time signals or continuous frequency signals. And for our DSP, we require discretized time signals. We saw in the previous lecture that we could convert a continuous time signal to a discretized time signal by using sampling. And as of such, we used the ideal impulse sampling where we multiplied the x of t signal here, continuous time signal here, with a set of impulse trains, with an impulse train, and we summed it up accordingly in order to get our sampling signal denoted as x of s of t. If we took the Fourier transform of this sample signal, given by the x of omega equation here, and we applied it into the equation of x omega, we see basically that we have an integral form here and a summation series here accordingly. We are also assuming linear time invariant signals and systems, so that's such we can separate out or combine integrals together. This property for linear time invariant signals also applies to summation series. So as of such, the summation series point can be placed outside that of the integral. If we recall what the shifting property is, we can basically see that it is quite similar here to this equation. And as of such, we can rewrite the xs of omega equation into this form here. Now note, when we moved from this form here of xs omega to this form here, we moved from continuous time here t to discretized time here n t of s. However, omega here is still continuous. So if we replace x n t of s here with x of n, and we say omega t of s is equal to capital omega, we move from the xs omega equation here to this form. And once we have it in this form, we can now say that x of capital omega is the discrete time Fourier transform for the discretized sequence x of n. Capital omega is referred to as digital frequency and it is measured in radians, whereas common omega is continuous frequency or analog frequency, which is also measured in radians. So we observed before that a sample signal basically had a periodic spectrum which led to spectrum replication, and the spectrum here was continuous for this particular instance. So actually, let's observe the property or the periodicity of the discrete time Fourier transform. If we recall the mathematical property for this, it needs to be such that x of common n is equal to x of common n plus capital N. So the DTFT spectrum is going to be periodic about a period of 2 pi radians. And we substitute this in accordingly to the x of capital omega equation. And we do all the math behind it and so forth. We basically are going to see that x of capital omega plus 2 pi, after we do all this math here, results back into x of capital omega, thus satisfying the periodic property here of 2 pi radians. The reason for this being that when we actually start doing the math here accordingly for these exponential forms, the exponential forms here, if you watch the Euler expansion, is such that e of minus j theta, where theta is 2 pi n, is equal to cos of theta minus j sine of theta. Because theta here is represented by 2 pi n, but for any instance of n here, for both the cosine and minus j sine terms here, you will always end up with a result of 1. Now, it's important to remember this Euler expansion that we're seeing here for e of minus j theta, where theta is 2 pi n, because we're going to be using this Euler expansion later on for a whole set of different applications regarding later lectures. So the spectrum produced by the DTFT is going to be periodic, and that it repeats itself every 2 pi cycles. Now, how does this compare with the spectrum replication in the context of sampling? Now, remember that we moved from common omega t of s into capital omega, where t of s was the sample period. And what this means is that we will map in that real frequency common omega to the digital frequency capital omega, which is going to be periodic with respect to 2 pi, which we just now observed by the graphical implementation on the previous slide. If we represent the highest frequency in the signal as common omega of h, the sample rate, being omega of s, needs to map such that omega h maps to capital omega equal to pi. And this satisfies the Nyquist rate. So capital omega here was equal to common omega multiplied by t of s. And then we're going to say that because we want the mapping to be satisfied, we want to let capital omega here equal to pi. Common omega here is going to be replaced by common omega of h. If we rearrange the equation accordingly to make t of s the subject of the formula, we'll get this form here. But we also know that t of s is equal to 2 pi divided by omega of s, being our sampling frequency. So if we equate this form here to this form here accordingly, and we do some juggling and substitution accordingly and rearrange the equation, we get that the sampling frequency here needs to be equal to twice that of the highest original signal frequency. And that satisfies our Nyquist rate theorem accordingly. Now if we took the continuous time Fourier transform of this rectangular window, as we've been seeing in the last few lectures, when we take the x of omega form here and we do the integral accordingly, what this results in is that we get a sinc function. This sinc function can be implemented in MATLAB. There's a sinc function it's explicitly used inside MATLAB if you're trying to implement it. The question here is, this is going to be continuous or discrete? And the name basically gives it away because you did the continuous time Fourier transform, so this is going to be a continuous signal. So if we plot the magnitude of the spectrum accordingly, we get our nice sinc curve, as we have been seeing in the last few lectures. Now let's actually observe what happens if we sample that rectangular window, and then we perform the discrete time Fourier transform accordingly. And we know that our sampling time here is going to be 0.2 seconds. If we applied it to a discrete time Fourier transform equation, being x of capital omega here, what we should obtain is this summation series here. Now the reason for this summation series is that this sample here is at 0, but this is going to be the first sample and second sample. This is going to be -1 and -2 accordingly. So this is how we get the limits of +2 and -2. Everything else substituted in accordingly for what we just observed for x of capital omega on the previous slide. We knew also that common omega multiplied by t of s is equal to capital omega, where t of s was the sample period. So if we substitute that into our x of capital omega equation, and we do the summation series accordingly, and we also apply the Euler expansion that we saw in the last lecture, x of capital omega here results in this equation. If we plot the magnitude of the spectrum, what we observe here is that we get a repeated spectrum accordingly. And this coincides with the property that we observed in the previous few lectures where the signal repeats itself. So notice the periodicity of the signal here and how it keeps on repeating. In this particular instance, the signal repeats itself at every 5 Hz. So if we compare our CTFT here with our 5-sample DTFT that we just now did, where the CTFT is the true form of what we're supposed to have, and the DTFT is going to be our approximation, there are a few differences that we need to observe. So the first thing to know is that notice how here that the signal here for the DTFT is shifted in the frequency axis, as well as it actually touches the frequency axis at distinct discrete points, being -1 +1, -2 +2, and -3 +3. But whereas with the continuous time Fourier transform, this actually doesn't occur. I also note that the zero crossing here is in between -2 and -3, and in between +2 and +3. So this illustrates that how the DTFT is a somewhat close approximation to the CTFT, and the approximation depends on the number of samples involved. So let's increase the number of samples and then reperform the DTFT on that rectangular window. And if we plot the magnitude, we basically see that the spectrum replication is done, but it's now it's more spread out. It's no longer at 5 Hz, it goes all the way down to like 10 Hz or something like that. And when we compare the CTFT to the 9-sample DTFT, which is the approximation, we can see that it tends to approach more towards the CTFT. So the more samples we have, the better the approximation is regards to how it's actually supposed to be. The less samples we have, the less approximate it's going to be. Now with accuracy, there's always a price, meaning that if you have more samples, it requires more computation time and more storage. So there's a trade-off that is involved when actually doing these transforms. So you actually have to balance how many samples you need, because in a real world scenario you don't have infinite space, and what is the minimum level of accuracy you absolutely require in order to achieve your intended outcome. If we compare the DTFT with 5 samples here to the DTFT with 9 samples, we also see how the 9-sample DTFT is more accurate than the 5-sample DTFT. Now, in comparing the resolutions, both of them are basically continuous spectra, and they resolve to the same frequency components, but there's going to be a slight difference in amplitude, however. And the number of samples being that if we have more samples, we improve the performance and accuracy of the DTFT. If we're wondering about the aliasing effect, the pulse basically has high frequency components that will not be sampled at the Nyquist rate. And if aliasing does occur, it will account for some of the amplitude differences between the spectra. So we saw the discrete time Fourier transform. Of course, an inverse discrete time Fourier transform exists. But this also means that we need to have an infinite sequence x of n for this to occur. So we may never use the inverse discrete time Fourier transform for this course. So if we start comparing the equations here accordingly for the CTFT and the DTFT. And the inverse CTFT and the inverse DTFT for continuous and discrete time signal. We see that they're actually quite similar. We just need to know what to substitute, and that duality behavior actually exists. If we apply it also to the Fourier series, we ought to see that duality behavior also exists for these equations here as well. If we take the Fourier series equations and we apply these limits here accordingly, what you can observe is that we'll actually obtain the discrete time Fourier transform pair as well. So our next lecture will show how we move from the discrete time Fourier transform to the discrete Fourier transform, and the lecture after that will show how we move from the discrete Fourier transform to the fast Fourier transform.